Oh, well, that's there. All right, I'll begin with a word of prayer. Dear Father, we just thank you for this day. Again, I thank you for this class, the time we have to study your creation. Just help us to understand a little bit more about vector spaces and distance and geometry and all this. And we just thank you again, Lord, for your many blessings to us. In your name I pray, Lord Jesus. Amen. Let's see here. So I think, oh yeah. Before we get to geometry, I still owe you some discussion of, so last time we were doing quotient spaces. I kind of indicated to you how we could find, the basis for the quotient, a basis for a quotient space of a vector space. So that's interesting. Of course, we could do an example. Maybe I can do a short example. Oh, no. The example is never short. Let me go on. So let's go on to invariant subspaces. Well, not even invariant subspaces, but let's talk about the direct sum. I want to talk about direct sum decomposition. All right. And I suppose before I even do that, maybe I should talk about a little kind of special discussion. If we're given, let's say, U and W subspaces of a vector space V, then we can define U plus W, right, as equal to, X plus Y, such that X is in U and Y is in W, right? Well, we can talk about how to add subspaces, take the sum of two subspaces, right? And of course, it's an elementary exercise to prove that this is in fact a subspace of V, right? What is a less elementary exercise is to calculate its dimension. All right, another thing you can talk about, of course, is the intersection of two subspaces, right? U intersect W. That is what it sounds like. It's X in V such that what? X is in U and X is in W, right? It's literally the set theoretic intersection of the subspaces. And again, you can prove that that is a subspace of V. So a typical definition I should, this was in my linear algebra course. I think it's in most linear algebra courses. Definition, V is equal to U direct sum W if V is equal to U plus W and U intersect W is just the zero subspace. This is the so-called direct sum decomposition. Of V. And in this case, U and W are so-called independent subspaces. Independent subspaces. Now we'd like to generalize this concept for more than two things added together, and it's a little bit subtle how that actually goes. But before I get to the generalization to three or more subspaces, we should just kind of rest and focus on the structure here and try to understand it, right? Because let's see if we can work this out. I'm probably going to get stuck on this because I haven't prepared, and this is a difficult thing. For me, difficult thing. So if you were to draw a big picture, right, there's something like, here's U, right? Here's W. And so I can talk about like a basis for U I can talk about a basis for W, right? And then of course there's U intersect V here, right? So a natural question to ask is, how does the dimension for, how does the dimension for U plus W relate to the dimension of U and the dimension of W? Do you know?
Will it be something like dimension of U plus dimension of W minus dimension of U?
You are correct. Now, what are you using there, though? You're really operating on basic counting, right? You're assuming that dimension works like cardinality. I mean, this is one of the first of many counting formulas, which are encapsulated more deeply in the inclusion-exclusion principle, which I don't know deeply. I gave a lecture on it once in a job interview, which was really, really dumb. Anyway, who cares about that? So, yeah, we subtract the dimension of the intersection because otherwise we'd be double counting it, right? But it's not. This is not cardinality, right? Because, of course, every one of these is infinite. There's infinitely many vectors in each one of these working over assuming we're working over a field of characteristic 0, right? Infinite field. So we're really, this has to be a statement about basis, right? So to prove this theorem, we have to somehow think about taking a basis and building it for U and U plus W, and we should try to build it in, in view of, so like I think what we could do is not be dumb and look at my notes. That's what we should do. This is the proof is on page 147 in my notes. Let's see here. So what do? I begin by picking a basis for the intersection.
You said 147.
Page 147.
Of the linear algebra.
Linear, yeah, 2019.
Yeah.
It's theorem 6.7.8 that I'm at. So let's see here. I start in the middle. I start with a basis for U intersect W. And then I adjoin it to get a basis for U. All right? So like I start with a basis for U intersect W, and I call that basis, I call that dimension, I suppose that's n-dimensional just for the sake of discussion. So I call the vectors in the vectors that, the basis for the intersection V1 through Vn. All right? And then I extend this to a basis for U. So I've got V1 dot 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 Vn, and then U1 dot 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 U UD, I guess. All right. So extending. Basis for U, right? And then I extend that to a basis for U plus V. U plus W, rather. U plus W. And I guess I use W's for this. W1, comma, da, 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 W, E. Now, of course, it could be that the basis for U intersect W is empty. Right? If V intersect W, if U intersect W is 0, then the original basis is just the empty set. Fine. Then the basis for U would just basically just be the u vectors, right? So then, all right, let's see here. But I make a more stringent case here, which is that the vectors, these vectors, by a theorem in the notes, I can adjoin these. These are in the W1 through WE are actually elements of what? These are actually elements of W complement the intersection. These, on the other hand, are elements of the intersection, right? Excuse me, these are elements of what? These are actually elements of U, right? Minus the intersection. And these over here are just elements of the intersection. So let's see here. Then what do I say? I don't understand why I have to prove it's linearly independent. I'm missing something logically here, because I'm proving that this I guess that okay. So well, there's something to quibble over here that I currently am like blinded to, maybe, because what I see here is maybe let me just keep talking. Sometimes when I talk, all of a sudden I understand what it is I'm missing. So what's the dimension with this, the dimension of U intersect W would be what in this notation, n, right? The dimension of U would be n plus d. The dimension of U plus W n plus d plus e, I suppose, right? And I guess if I know that this is indeed a linearly independent set which spans U plus W, I think the theorem follows immediately. So the calculation I have on page 147 is proving that the basis so constructed is genuinely linearly independent. Like I'm not.
But shouldn't we have B plus? Okay, I see.
So then, yeah, I mean, if I just calculate the dimension of U plus W, well, that's equal to n plus d plus e, right? Which is equal to n plus d plus n plus e minus, my bad, n plus d plus n plus e minus n, right?
Yeah.
Which is exactly the dimension of U plus the dimension of V minus the dimension of the intersection.
And we need linear independence to show that is in fact a basis.
Right.
A plus W.
And so I think, let me just sit down here for a second. The proof on page 147, if we look at it, I pick Z and U plus W. I say, okay, well then that means X is, it can be written as X plus Y, where X is in U and Y is in W. I expand X in the basis for U, and I expand Y in the basis for W. And then I collect the terms which are from the intersection part of the basis. I set it equal to 0 in equation star. I solve for the vector in W, which I guess is minus Y there. And I show that vector is in fact in the intersection. So that means I can write it I feel like I found this proof in Curtis's linear algebra once upon a time. Curtis, which is a very good book. But I wonder, I don't see currently why, what I'm confused about, Ernesto, is why I need to prove linear independence. Because we have a theorem that says that if we have a subspace, we can choose a basis for it. And then if we wish, if that subspace is a subset of another, so this U intersect W is a subspace of the vector space U. And as such, I can extend the basis to a basis for the whole space. And I can keep the same vectors in here, right? And then this is a subset, this is a subspace of U plus W, which means I can use the extending the subspace theorem again. And so if I have this theorem that I can take a basis for a subspace and I can extend it to a basis for the superspace in which that subspace resides, I already have linear independence of the basis constructed. I don't need to prove the linear independence. So I don't understand why my notes are proving the linear independence if I already have that theorem. Perhaps I've lost track of my notes, like what's been proved at this point. But it seems to me a more logically efficient way of proving this is to have already proved the basis extension theorem and simply apply it twice. And then once you do that, the counting is immediate.
That makes sense.
I don't, forgive me if I'm glossing over something, but I think that that's logical. But, errors in linear algebra are oftentimes very seductive. So. All right, so the next section in my notes is just a recap about systems of equations, like the homogeneous and the particular solutions and how that works. You can look at the solution set to systems of equations in view of the quotient space idea and say things there that are kind of interesting. The solution set to a system of equations really is a quotient space. Let me be really terse about this. If I'm thinking about AX equals to B, and I'm talking about like A is a matrix, B is a fixed vector, and I'm trying to describe what the solution set there is. Well, the solution set is not a subspace, right? It's not, because if B is non-zero, the sum of solutions is no longer a solutions, right? It's not a subspace. However, you can write X as equal to, let's say, X homogeneous plus X particular, where what? The homogeneous solution is 0, right? And the particular solution is B. So if you really look at that, what do you got? So the solution set is what? It's simply the particular solution plus the null space of A. And if you want to think about it, if you think about all possible n-dimensional column vectors, they all fit into a particular solution space corresponding to what the particular solution is. And as it turns out, like where you are for to pick a specific solution in this context, you need to be given a set of initial data, right? To pick constants, to pick out the particular element of the null space that fits your problem, So just a brief remark. This is kind of at best tangential to what I'm mostly talking about today. All right. But it is in my notes, so I figured I'd. So I would say that the solution set is what you might call a linear manifold. And so I talk about a directing space. So this would be an example of a linear manifold. The directing space of this linear manifold would be the null space of A.
Just 6.8.
Yeah, that's definition 6.8.7. And proposition 6.8.9 is basically saying what I just claimed. And then example 6.8.10 is fleshing what this actually looks like for a specific example. And then what is 6.8.11? V a finite dimensional vector space, W a subspace of V, P plus W is a solution set. Oh, now 6.8.11, proposition 6.8.11 is something actually kind of interesting, which would stop most linear algebra students in their tracks. So you've got W is a subspace of V, right? Then P plus W, right, is a linear manifold. In V. And there exists, equations let's just say there exist equations for which P plus W is the solution set.
How do manifolds come into the discussion?
Well, the definition is in the start of 6.8. I just said that a quotient space is a linear manifold, is all.
Quotient space is okay.
Yeah. The reason, so here's the difference, Ernesto, between a subspace and a manifold. A linear manifold, I don't have any expectation that the origin is in there. So in terms of like the ambient vector space structure, it doesn't have to be a subspace. However, a linear manifold could be made into a vector space simply by adapting the definition of vector addition as appropriate to like being on the, basically you think about vectors anchored to the subspace versus anchored to the origin. And then if you add the vectors on the plane appropriately, you get other vectors on the plane. So yes, it's not technically a subspace of the ambient vector space, but there's a kind of obvious way to make it into a vector space where essentially you make the point at which it's attached the origin, for example. But of course that choice is not unique. Like you could make any point on on the linear manifold origin, and you'd have a different vector addition there. Certainly isomorphic to a subspace. But anyway, this is kind of a more interesting claim. I'm saying that if you have a quotient space to a vector space, there exists a system of equations which it's the solution set for. So then that begs the question, if I give you an example, right, what are the equations for which it is the solution set? That's a kind of tricky, backwards kind of question, like, you know. But it's the heart of the problem of, you know, parametric versus implicit. How do you go, oh, I think I'm in the wrong chapter. We were in chapter 7, weren't we? How did I get back to chapter 6? What just happened? I'm a dummy.
That's great.
It's okay. Yeah, it's okay, actually. It's for the best.
I think we're going to start chapter 9.
Yeah, that was
Go back to 8.
something like that.
Because 8 is eigenvectors.
All right, so yeah, I was trying to talk. So we were talking about quotient space. The first isomorphism theorem is right after that. Like, let me just show you a quick example of this in practice that's really hard. Maybe it's hard. I don't know if it's that hard. So, for instance, we could look at W, you know, V equals to, like, you know, second order polynomials over the reals. We could let W be equal to, like, T plus the span of 1 and T squared, you know. Well, this wouldn't be W. This would be T plus W, all right? So here's my W. My claim is that there is a system of equations which that's the solution set for. So a typical element, if I, you know, take, say, F, an element of T plus W, what's it look like? Well, you got F, you know, equals to T plus what? Like C1 times 1 plus C2 times T squared, right? So how would you figure out equations for which this is the solution set? Well, what you could do is you could say, okay, well, let me see here. If I'm going to say F is equal to T plus C1 plus C2 T squared, right? Let me set that equal to generically, like a generic point in P2. What's a generic point in P2? Let me use X, Y, and Z. I'll use X, Y, and Z for, you could use like other numbered coefficients, but I'm going to use X, Y, and Z, all right? So I have X plus Y times T plus Z times T squared. So the kind of equations I'm looking for are equations in X, Y, and Z, if you like. So then we can equate coefficients, right? And I'd get what? I'd get, like, apparently X equals to C1, Y equals to,
That's supposed to be a T squared.
that's a T squared.
Yeah, on the other side.
Yes, thank you. My bad, C sub 2. I mean T sub 2. What on earth? All right, anyway, so X equal to C1, Y equal to 1, Z equal to apparently C2, right? So these are free. Nothing really to do there, right? You're not going to have an equation that involves Z, but you know, t plus w is actually what? It's actually equal to the set, right? X plus yt plus zt squared, such that what? Well, such that x and z are elements of the reals, and y is equal to 1. Which you could, of course, write as what? You know, you could express that as like 1. I mean, you could express it as t plus the set, you know, x. Sorry, my notation right now isn't the most awesome. There's like a better way of saying all this, but this is what I'm coming to at the moment, okay? Like this right here is this so, oh, in other words, the subspace, right? I mean, this is the heart of the matter, is that you can express so this is expressing the subspace parametrically, right? A typical point in W is written as a linear combination of the generating set 1 and t squared. You give me parameters C1 and C2, I give you the vector in W. Down here, I'm describing W as the solution set of an equation, right? Which x plus yt plus zt squared are in this set? Well, the ones which solve the equation y equals to 0. That's different than that. This is a solution set viewpoint, or I would say an implicit viewpoint. That's a parametric or an explicit viewpoint. We've always got these two different viewpoints battling. So manifold theory is the abstraction of the parametric viewpoint. We talk about how to, like, you know, parameterize these abstract spaces, right? Actually, truth be told, in manifold theory, we look at charts which go the other way. They're actually the inverse of a patch. They start in the abstract space and they map back to Rn. But it's still very much in the parametric perspective, right? The other side of things, describing abstract spaces as being arbitrary elements of the abstract space subject to, you know, a collection of equations, right? Like common equations holding true. That's the implicit viewpoint, and that is what usually gets called the study of varieties. A variety is like a solution set to a collection of multivariate polynomial equations. So if you want to describe abstract spaces in terms of like a bunch of equations, the common solution set to a collection of equations, that's more the variety viewpoint, which I am less versed in. That's algebraic geometry. And the variety viewpoint, since it's so easy to understand equations over other fields of numbers, there's a lot of like theory of varieties that you can do varieties over like finite fields and things, and there's so much there to learn. Some of the most abstract mathematics that's been done in modern times has been done in that realm. But anyway, the word manifold and the word variety are just two different translations of the same original German word used in Riemann's big talk he gave when he became a professor. When you become a professor in a German university, you have to give this like magnum opus talk about this is what I'm about, this is what I'm going to do. And when Riemann gave that talk, he gave basically, this is what an n-dimensional manifold is, and we need to study its properties. And he set the stage for manifold theory in about 1860. And he died not too long after. He died pretty young. It was left to others to discover like the full calculus of manifolds later. And I don't think it was like terribly big focus of mathematics until general relativity came along, and then all of a sudden the equations which had been, like the calculations which had been discovered in that kind of mathematics were all of a sudden needed for Einstein's relativity. And they'd just been sitting there for him to discover, the work of Reggie and Levi-Civita and others. But anyway, I digress. So let us get back to, if you don't mind, I'm not going to talk about the first isomorphism theorem right now. I don't know if I want to talk about it in here either. I really should talk about it for the sake of you being best prepared for graduate school. It's definitely something you should read.
Which section is that?
7.8.
Okay, I'll read that.
Maybe some other day I will, feel up to it. Well, I don't know if I need that at the moment. I'm a little worried about skipping past section proposition 7.8.23. Let me just write that out. If I can. So there, I have so basically I have a linear transformation from a vector space V to a vector. So it's an endomorphism from V to V. And we have U is a subspace of V. All right, U is subspace of V. And what else? It's what's known as an invariant subspace. An invariant subspace of T. So what that means is that T of U is back into U again. So this is my proposition 7.8.23 in my 2019 linear notes. This makes U what's called an invariant subspace. All right. Suppose you got all that. All right. And so then I take a basis for U. And extend to beta equals to beta U, intersect beta, union rather, beta 1, a basis for V. All right. So then this proposition is just talking about what does the matrix of T look like with respect to such a basis, all right? So first of all, you notice that we can talk about T restricted to U. That makes sense, right? Because that's a mapping from where to where? It's a mapping from U to U, right? Does that make sense? Because if we restrict the domain to just U, since it maps to U, that is itself a well-defined endomorphism. And so we can talk about A equal to the matrix of T restricted to U with respect to the beta U basis. What a horrible notation, but there it is. Okay? I should start putting the weak markers on the other board so I stop using them. Now, the other thing we talked about, right, was that if we take the quotient of V by U, right, it's actually equal to the the span of let's say I don't know, goodness gracious, v plus u such that v is an element of beta 1, right? Remember I talked about if we have a quotient space, we want to form a basis for the quotient space. We take the part of the basis which is not forming the basis for the subspace by which we're dividing and setting to 0, and those plus the subspace form the basis for the quotient space. We got that. And then I define something called T. I have yet another notation. By the way, it's really important in terms of just calculational mastery to be able to get back and forth between the parametric and the implicit viewpoints, because some things are much, much easier in one viewpoint than the other. For example, it's kind of a drudgery to figure out intersections of subspaces if you're given the subspaces in terms of spans. Because you're left with the question, so which of the things in the spanning set are in the other set, you see? And it's not enough to just check if the vectors themselves are matching with the other thing. You have to check if they're in the span of the other thing. It's just troublesome. On the other hand, if you want to calculate the intersection of two subspaces which are defined by equations, you just combine both equations at once. You just stack the equations and impose all of them. That's the subspace. So like intersection can be much easier in terms of equations. There's things to be careful about when you're looking at intersection of subspaces in terms of spans. Those make good qualifying linear algebra questions if you ask them in the right kind of nefarious way. All right, anyway, so what do you think T sub V mod U should be equal to? Like this is going to be, we're going to define a mapping from the quotient space to the quotient space built from T. And what we're going to do is that this thing, if we let it act on, let's say, x plus u, what do you think it's going to be equal to? So this is a definition. We can, what I'm saying is if you're given a linear mapping on the vector space, you can induce a mapping on the quotient vector space according to the simple rule.
You said if you gave a mapping on the quotient space?
I mean, I'm given that T is an endomorphism. T is a mapping from V to V. I'm defining a new linear mapping.
From the quotient space to the quotient space.
Yeah. So what you do is, well, you know you're going to have a plus u over here, right? So what do I put here?
X plus x? X.
Mm-mm. It's got to be based on T somehow or another.
Okay. What do we know about it?
There's almost, we don't know anything. It's just a linear transformation. There's only really one thing we can write down here.
T of x.
T of x, yeah. It's inescapable, right? That's the only thing you can write down here. I mean, I guess you could write x down, but that wouldn't have anything to do with T, so that would be kind of annoying. And so the point is, then you can calculate the matrix of T. It turns out you can prove this is linear. It's almost obvious that it's linear, but you can prove it. That makes a super friendly undergraduate linear algebra question. And then, of course, you can calculate the matrix of this thing with respect to the basis of the quotient, right? Man, that's a lot to write. But if you call this matrix, well, you can call that matrix, I think C. I called it C. All right. Then the matrix of T overall with respect to the beta basis. It has a block diagonal decomposition. It looks like A, you got the C down here, and then B up here is just whatever. This is 0. So invariant subspace is really nice because it means that you've got like, it's just going back into the subspace. So if you build a basis which respects that structure, you're going to get zeros under the part which is not from the subspace. Yeah. And whatever there is to prove there, I prove, you know, right there. There's really not much to prove. It's just a question of how we define basis and sorting through things. Now, what would it mean though? Like, corollary to this essentially, and this is really more the point of what I wanted to get at today, is that if V is equal to V1 direct sum V2, right? Then you could have the matrix of T with respect to the beta basis. It'd be block diagonal. It'd be like the matrix of T restricted to V1 with respect to the beta 1 matrix basis. Zeros here, and then the matrix of the restriction of T to the V2 space with respect to the beta 2 basis. And, well, it's not just this, right? What else do I need? So here I'm assuming that, you know, this has basis beta 1, this has basis beta 2. And what else am I assuming for this corollary to be true? How do I know that when I feed T vectors from beta 1, I'm just back in the span of beta 1 again? Which is what I'd need for this to be 0. And how do I know that when I feed T, I only get vectors in the span of beta 2 again? I've got nothing in the beta 1 span again. Well, I need to assume that V1 and V2 are both invariant subspaces of the linear transformation. So I need like T of VI is a subspace of VI for I equals to 1 and 2.
Is corollary in the loop?
No, it's just a comment after the proof, right before section 7.9. It's on page 206. Okay, so let us continue on here. Now we have more to say about invariant subspaces and their matrices in a future meeting, but today I'm trying to focus just on the concept of independent subspaces. All right, so there's something fussy here that has confused me at times in the past, and it need not confuse us. It's one of these things where linear algebraists, they say they're the same thing. And they do have the same structure. But if you're a person who thinks about sets and about points and about objects, they're not the same set. They're not the same object, but they are isomorphic. So you just have to be wary. And unfortunately, like, the notation is just unkind to undergraduates who are, you know, not initiated in this wild world of conflating things. But I said direct sum, but perhaps it would be better for me to add the term internal. And the reason it's an internal direct sum here is because those are subspaces which are a subset of V. I'm assuming U and W are subsets of V. There's also an external direct sum we can talk about. So let's talk about that. So this is my section 7.9. All right, so I'm going to erase all this.
So the external would be like a cross, like you could be on there.
So the external direct sum would be, you know, given, I'll stick with the notation in my book, given vector spaces V and W, V cross W. Right, we could take the Cartesian product, as you know, right? And that is a vector space. And this is actually the external direct sum of V and W.
I wrote a paper on the internal and the external direct sums.
Oh, okay, good.
In abstract, so I don't very well.
So it's, you know, the thing that's annoying is like people will write this. But that doesn't, technically speaking, even have to make sense in the way we were just talking about it a second ago, because it may be that V and W are not common subspaces of a given superspace. Like, it could be that V has matrices and W is functions from the unit interval, subject to some differential equation or something, right? I mean, whatever. But this is nevertheless a new vector space that we can form given vector space V and vector space W, right? You know how to define the addition, right? The addition is defined component-wise, right? If we have xy plus, you know, vw, by definition it's x plus v, y plus w, and c times xy, by definition cx, cy. All right, great. Then what would be the basis? So theorem, right? If beta v equal to v1 dot 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 vn and beta w equal to w1 dot 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 wm are bases for v and w respective. Then, you know, beta v cross w equal to what? Like, what? How can we form a basis for v cross w?
V1, W1. That's, I mean, the pairs.
I mean, I guess if you'll allow me this kind of abusive notation, we could do beta v cross 0. I mean, this is not an abuse of notation. This is just, I think, right. I think this is right. Union with 0, Cartesian product with the beta w basis. My bad, that was a union of these two sets. To be more explicit, what we're looking at is like v1, 0, dot, 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 vn, 0, and then 0, w1, dot, 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 0, wm. That's a natural basis for the external direct product of v and w. Now, if you once we've proved that's a basis, what do we see? The dimension of v cross w is equal to dimension of v plus the dimension of W, right? Because this is N, this is M. So the proof that that's a basis is, kind of fun to go through. It doesn't take long. If I've got X and Y, right, I can rewrite that as a sum of, let's say, Xi, Vi, sum Yj, Wj, I equals 1 to N, J equals 1 to M, right? So this is for an arbitrary point in the eternal direct sum. Then by the definition of the vector addition here, what happens? And pull the sums out, right? And so basically you can rewrite this as a sum over I equals 1 to N of Xi parentheses Vi comma 0 plus the sum J equals 1 to M of Yj 0 comma Wj, right? Which is obviously an element of the span of my alleged basis for the Cartesian product of V and W. So it's a spanning set. And then linear independence, well, if you set this equal to 0, right? If you'll allow me this small manga style calculation, excuse me, manga style. If I set this equal to 0, 0, right? Then that means that this has to be 0 and that has to be 0 independently, right? That's the very construction of the Cartesian product. Independence of the things you're producting. I mean, you can ask the question, how is that possible? And if you want, you can do this all with sets of sets, and who cares? There is a set theoretic construction for Cartesian product, which we never really talk about in classes. It's out there. But if this is equal to 0, then linear independence of the basis of V gives me the vanishing of all the coefficients X sub I. And then linear independence of the basis for W gives me the vanishing of all the coefficients for W sub J. Consequently, I have vanishing of all the coefficients, which means that I have, indeedly doodly, setting this equal to that, like this linear combination equal to 0 forces that and that, all of those to be 0. Linear independence is what we have. All right, so this is the Cartesian product of two vector spaces. And of course, I think if they were infinite dimensional, this is still a basis. It's just then I can't number them, So, but the most fun things I have to say in finite dimensions. Any questions? Or?
Well, I was going to ask, so minus the external and internal direct product, the same direct sum.
They would not be equal as sets.
Not as sets, but when are they isomorphic fully?
In the context that you could, suppose V and W are both subspaces of a given superspace, of a given vector space, right? It would not be true that V direct sum W, internal direct sum W, is equal to V Cartesian product with W. The question you're asking is when, okay fine, but when are they isomorphic? They would be isomorphic when V intersect W is 0.
Okay.
So they're isomorphic. They would be isomorphic when the subspaces are independent. And that's the heart of the matter. Is like the idea then is really that if you're given a collection of subspaces, of a vector space, then those spaces are independent if and only if they are isomorphic, if only if the sum of them is isomorphic to the external direct sum of them is in the sense of Cartesian product.
So the internal and the external are isomorphic if and only if the spaces are independent.
In the context of the subspaces being common subsets of a given vector space, we can say that. But the external direct sum has a context which is beyond these being subsets of a common vector space. If they are,